Hi, I'm Lisa Weiland with the Wabash Valley Astronomical Society. Today we're going to look at some accessories that commonly come in beginning telescope packages, as well as some other useful accessories. Some accessories are necessary, like eyepieces and finders. Others have degrees of usefulness based on individual tastes and needs. We'll start with eyepieces and Barlows, and then we'll look at finders and other things.
What is an eyepiece? An eyepiece is a combination of lenses mounted in a tube that you use to view and magnify the image formed by the telescope. They're sometimes called oculars. The lens closest to your eye is called the eye lens, and the one closest to the objective inside the scope is called the field lens. The eyepiece does not produce the image, it just magnifies the image formed by the telescope. So, welcome to the halls of power. When you want to know what power your telescope has, what you're really asking about is magnification. How many times is what you're looking at magnified? Different magnifications are needed for different types of objects. Magnification depends on the combination of telescope and, also importantly, eyepiece. The eyepiece you choose is what determines how much magnification you're getting. To see how this works, you first have to understand the concept of focal length. There will be some math involved, but it's only 4th grade level, and you can use a calculator if you want. There are no pop quizzes here. When light passes through a convex lens, it forms a cone shape that comes to a focused point at some distance from the lens. That distance from the surface of the lens to this point is called the focal length. A curved mirror will also have a focal length, like in reflector telescopes. Magnification is calculated by dividing the focal length of the telescope by the focal length of the eyepiece. You need the telescope's focal length in millimeters to keep the units the same as the eyepiece units, which are always given in millimeters. Your telescope's focal length does not change, but you can change the eyepiece focal length just by changing eyepieces. So our first example here, right under the cone there, shows that we are looking at a telescope with a focal length of 900 millimeters, and we're using an eyepiece of 25 millimeters. So our magnification is 900 divided by 25 equals 36 times. As a second example, suppose you use a 10 millimeter eyepiece with that telescope. Now you have 900 divided by 10 equals 90 times magnification. Big difference, just by changing the eyepiece. So we saw that a 900 millimeter telescope with a 10 millimeter eyepiece in gives a magnification of 90 times. With a 30 millimeter eyepiece, we get 900 divided by 30, or 30 times.
Why would we want to reduce magnification? The answer is field of view. There are 2 types of field of view, apparent and true.
Apparent field of view is how wide the eyepiece's field of view appears when you look through it. So, apparent field is how many degrees of sky that it looks like you're seeing as you look all around the entire field in an eyepiece. The true field is the actual angular extent of the sky you can see with any particular scope and eyepiece combination. That is, how many actual degrees of sky you're seeing with any scope eyepiece combination. There is a formula to calculate the true field, but I will give all the formulas for true field and other things that we're talking about at the end of the eyepieces and Barlow segment. Longer focal length eyepieces of the 25 to 40-ish millimeter range give you a wider field of view. And here we're talking about true field. Shorter focal length eyepieces, 3 to 10 millimeters, give you higher magnification, yes, but you're seeing a much smaller apparent field of view through it. In this example, longer focal length allows you to see the entire moon in your eyepiece, while the smaller focal length allows you to see only a tiny part of the moon in greater detail, but a much smaller part. Having a wider field of view is a very good thing when you're looking for an object. Once you find your object, you can change eyepieces and get a more detailed view. When looking for an object, this is the drill. This is what you will always do. Look for it with the longer focal length wide field eyepiece. After that, you may or may not decide to look at it with a shorter focal length small field eyepiece. Many nebulae, star clusters, and galaxies look about the same with a shorter focal length eyepiece, but you see less of them in your field of view. So the longer focal length and wider field actually turns out to be the better view. Sometimes with eyepieces, less is more. High magnification is generally best for solar system objects, like the planets and the moon, or splitting double stars. But even with these objects, for any telescope, there's such a thing as too much magnification. At lower magnification, objects are brighter and sharper. As magnification is increased, they become dimmer and not as sharp. The telescope only gathers a fixed amount of light. At higher magnifications, the same amount of light is being spread over a larger area, resulting in a dimmer image, and you're just reaching a point where you're magnifying a blur. There's a rule of thumb for determining how much magnification is really reasonable for a given telescope's image. It's inches of aperture times 50 equals your maximum useful magnification. For example, if you have a 2.5-inch aperture scope, you can use an eyepiece that gives you up to 2.5 times 50 equals 125 times magnification. If you try to go beyond that, you'll be magnifying the blur. This is why tiny telescopes that promise stupendous views with 600 power are total frauds. If you use an eyepiece that gives you a magnification of more than 125 times with a 2.5-inch scope, you'll be looking at a small, dim, blurry spot. The magnification provided isn't the only important property to consider in an eyepiece. There's also something called eye relief. This is the distance from the eyepiece lens to the point where your eye can best see the full field of view. This distance can range from 2 millimeters to 20, depending on the design and focal length of the eyepiece. This becomes an important consideration for people who wear eyeglasses because they generally need about 15 millimeters of eye relief to be able to use an eyepiece. Those who don't wear glasses can get by with much less. As low as 10 millimeters can be perfectly comfortable, while eye relief values less than that can have you nearly setting your eyeball on the eyepiece surface to try to use it. So eye relief is generally a comfort consideration, but people who wear eyeglasses may find short focal length eyepieces unusable. These are all schematics of different eyepieces showing the lens elements in each design. To combat shrinking fields of view with magnification, improve eye relief and apparent field of view, as well as multitudes of other considerations like field flatness and corrections of various lens aberrations and reflection issues, eyepieces come in a mind-boggling assortment of designs. Here is a small sampling. Some can get quite large and heavy, and the prices can be, well, Astronomical. We've recommended a Plossl design because it's an excellent performer in terms of both apparent field of view and eye relief at longer focal lengths. Shorter focal length Plossls can have shorter eye relief, but I wear glasses and have found I can still see through my 9 and 10 millimeter Plossls just fine. Here is a list of popular eyepiece types with their apparent fields of view and an estimation of what that amounts to visually. Now, since we don't know the focal length of the telescope or eyepiece used to take these pictures, you shouldn't think that, for example, a Plossl won't show you the whole moon in your scope. Whether or not it does depends on the scope. This is more of an example of how apparent field of view changes with wider field eyepiece designs. We've recommended Plossls as a good starter eyepiece because good quality ones offer a decent apparent field of view and a flat field with good contrast, brightness, and excellent sharpness of your image. They're useful for most purposes, from short focal lengths for planetary, moon, and double star views to long focal lengths designed for deep sky views. And they come at reasonable prices. Kellners are a 3-element lens and have some color fringing issues, but you will find them included with some beginner level telescopes. As eyepieces for young kids, that'll be all right, but if your child's interest in the hobby grows, you may eventually need to invest in some Plossls. We've harped on anti-reflective coatings in our overview video, and we've mentioned them here. Here's why. Uncoated lenses reflect up to 10% of the light trying to pass through them. That means a dimmer image. Coated lenses allow more light to pass through the eyepiece, giving brighter images and reducing the amount of light that's scattered within the eyepiece. This allows for higher contrast. Good quality eyepieces are labeled multi-coated, which means that at least one surface of the lens was treated with multiple layers of anti-reflective coatings. Your best quality eyepieces are labeled fully multi-coated, which means that all air-to-glass surfaces are multi-coated. Magnesium fluoride is the most widely used material for optical coatings. You can see if an eyepiece is coated. Just hold it under a light and you should see a bluish, purplish, or greenish reflection on the lens. It should not look white.
To get started in the hobby, you can get by on just 2 eyepieces, one long focal length and one short. That is, one wide field and one higher power small field one that will give you a more detailed view. Sometimes your eyepiece package includes one eyepiece and one Barlow. Let's look at those.
What is a Barlow? A Barlow is a system of lenses in a tube whose ultimate effect is to increase the focal length of your telescope, usually by 2 times. There are 3 and even 5 times Barlows out there, but those are really intended for use with webcam photography. For visual observing, a 2 times Barlow is the standard. A Barlow is placed between your focuser and the eyepiece. There's a negative lens in it and some other lenses to correct chromatic aberration, the problem of different colors of light coming to a focus at different distances from the lens. Their ultimate effect is, as we just said, to double the focal length of your telescope. So what does that do for you? Remember our 900 millimeter telescope with that 25 millimeter eyepiece in it? With that set up, we got a magnification of 900 divided by 25 was 36 times. With the 2 times Barlow in, our 900 millimeter telescope now has a focal length of 1800 millimeters. So with that same eyepiece, we now get 1800 divided by 25 and get 72 times, all while keeping the same eye relief of the 25 millimeter eyepiece. So instead of putting 2 eyepieces in a telescope package deal. Many vendors just put in 1 eyepiece and a Barlow because it's almost the same as putting in a lower magnification wide field eyepiece and a higher magnification smaller field eyepiece at less cost to them.
But it's really not quite as good as 2 different eyepieces. Why? 1, a Barlow adds more weight to the front end of your scope, changing its balance. And more importantly, 2, a Barlow is an additional bunch of lenses for light to pass through. Each lens element both reflects light from its optical surfaces and absorbs light internally. So ultimately, less light finally arrives at your eye, and the image with the Barlow is a little dimmer than the image through a different eyepiece alone would be. There are really high quality Barlows available that provide a good image, but these are usually in a higher price range, and by the time you're spending the extra money on a Barlow, you might just be better off investing in another eyepiece. On the other hand, if your telescope comes with 1 or 2 eyepieces, neither of which gets you close enough to your scope's maximum useful magnification to suit you, you might do well to buy a Barlow to get more out of the eyepieces you've got. 1 Barlow doubles your whole eyepiece collection.
Your telescope and eyepiece are only looking at a very tiny part of the sky. In order to get your object of interest in the eyepiece, you need a finder. This shows you a section of the sky that should include your object. Finders come in 2 stripes, ballpark and pinpoint. We'll start with ballpark. Ballpark finders are finders that can get you spot on bright targets like the planets and the moon, or near, harder to find deep sky objects. We'll start by looking at dot finders. Dot finders don't magnify what you see, but they make it look like a dot of red or green light is being projected onto the dark sky. If your dot finder is aligned parallel to your optical tube, then wherever the dot appears to be in the sky, the telescope will be aimed at the same place.
Most dot finders have up, down, and left-right adjustment screws for alignment of the dot with the optical tube. Allen wrenches are often needed for this alignment. This can be hard to do in the dark. Alignment should normally be done during the daytime hours or at twilight.
Good dot finders use LED lights that can be brightened or dimmed as necessary. Some even let you change the dot to a crosshair, bullseye, or other shape. Here on the right is the famous Telrad finder that projects a dimmable bullseye onto a 4-degree field of the night sky. On the left is another dimmable dot finder with an assortment of target patterns available. When the target isn't dimmable, it might be too bright, thereby preventing you from seeing your object of interest in the finder's field.
A disadvantage of dot finders is that they can lack accuracy in locating objects that are not visible to the naked eye. Also, when you're looking for items high overhead, you can have to assume impossible positions to use them. This is where a green laser pointer can have an advantage.
Green laser pointers are a tool you can use to point out stars to other people, but they can also be used with your telescope as a ballpark finder.
But first, there are some green laser pointer caveats. 1, they have a potential for serious eye damage. Their unfortunate resemblance to lightsabers from Star Wars makes kids want to play with them like that, but these are not toys. Green laser pointers cannot be pointed at any sort of airplanes or helicopters. It's a federal crime to do so that carries a maximum of 20 years in prison and a $250,000 fine. And the FBI has ways of finding you if you do this. There are also laws with fines and jail sentences for other definitions of laser misuse that vary by state. For example, here in Indiana, it's illegal to point a green laser at any stripe of lawman, a sheriff, policeman, state police, etc. And Illinois has a bunch more laws. So in general, green laser pointers are not recommended for children. If you do allow your child to use one, make sure it is not stronger than a 5 milliwatt instrument. And 2, do so only with adult supervision, especially if your kids' friends are over or their siblings are involved. I know this depends on the child, but be aware that parents are responsible for the actions their children take. All this said, used responsibly, green lasers make great ballpark finders. I use one in conjunction with my wide-angle correct image finder scope to rapidly find deep sky objects. There are mounts you can get to mount your green laser to the scope, but you really don't need one. As long as you have an edge to lean the laser on that's parallel to your optical tube, then that's good enough. You could just tape any sort of straight edge to your scope for this if your scope's focuser doesn't already provide you with this convenient little resting spot for one. If you do that, tape something to the scope, then the laser has to be parallel to the optical tube. Now, to create something that's parallel to the tube, you'll have to start from working with something that's perfectly perpendicular to the front end here. A green laser used like this isn't perfectly aligned with the scope, but you just need to nudge your scope in the direction the laser sat to bring your object into view. If you have a pinpoint finder, like a finder scope, then you don't even need to do that because the rested laser's beam brings you close enough to see the object in your finder's field of the scope.
Pinpoint finders are small refractor telescopes with 8 or 9 times magnification, sometimes less. They should have a set of crosshairs at the objective end to allow accurate focusing on a star. Pinpoint finders are used by developing star hops, that is, paths of stars comprised of simple shapes from a bright star to your object of interest. This takes a bit of homework with star maps. When used in conjunction with ballpark finders, celestial objects can be found sometimes in seconds. The right angle on the RACI finder makes the small scope easy to use when the main telescope is pointing up at a variety of different angles. The corrected image part means the view in the finder matches the view on a star chart. Without it, the finder views upside down from charts, which can drive people absolutely crazy in no time flat. I wanted to say that the straight finder in this image looks like it has a right angle part at the back, but that is the control for the illuminated reticle on the inside of it. It's not where you look through.
Sometimes straight through finders are what you want instead of right angle. If you have, in particular, catadioptric scopes, where you're already at the back of the telescope to see through it, if you have one that's very high, like mounted on a pier or on a tall tripod, oftentimes a straight through finder is more convenient for you to look through than a right angle one. It just depends on your individual needs and your telescope's situation. The bottom line on finders is everyone needs a ballpark finder. Whether you need a finder's scope depends on whether or not you're interested in developing star hops to find objects not visible to the naked eye.
We just wanted to correct a small error in the overview video about Crayford Focusers. In that video, I said they allow coarse focus and fine. Well, those are the dual-speed Crayfords, but there are mono-speed Crayfords. The Crayford design reveals itself by the flat surface that's machined into its draw tube. It uses a direct metal-to-metal and surface-to-surface drive mechanism that allows for very fine adjustments, whether in mono or dual speed, making these focusers outstanding for both visual and photographic work. In this picture, you can't help but notice the large, round, silvered object to the lower right, nor the colorful collection of circles on the white piece of paper to the upper left. These items are filters of various types. We'll start with the large silver one. This is a solar filter. Solar filters are used to safely observe the sun in the daytime. There are several types of solar filters: white light, hydrogen alpha, more commonly known as H-alpha, and calcium K-line filters. White light filters are suitable for beginner solar observers. The other types of filters produce fabulous views of the sun, yes, but they're very expensive. Here are three types of broadband, that is white light, solar filters: polymer, glass, which is actually metal on glass, and Bader film. The advantages of the polymer filters are that they produce a nice yellow-orange view of the sun while being highly resistant to getting holes or scratches. Glass filters also produce nice yellow-orange images of the sun, but are more susceptible to scratches. Bader film produces a cool white image of the sun. All of these filters show sunspots and solar granulation in the solar photosphere. Here are examples of sun images. The one on the left demonstrates how the sun appears through polymer and glass filters, and the one on the right demonstrates how the sun appears through a Bader film filter. While not exhibiting the yellow color, the Bader filter still shows you sunspots and granulation. These filters fit over the front end of a telescope and block 99.999% of the light and all of the harmful ultraviolet light. They're entirely safe, but should always be checked for any holes or scratches before use. We do not recommend these for children without strict adult supervision, period. Telescopes in general should never be aimed at the sun unless one of these over-the-objective type filters are in place.
If you run across any eyepiece that claims to be a solar filter that's to be used with nothing over the front end of your scope, throw it away and break it into a billion pieces first. Any filter in an eyepiece alone pointed at the sun can crack and break, and in the instant that it does, the eye you're using with it is blinded instantly and forever. A telescope should never be pointed at the sun without a quality solar filter over the front end of it. Placement of the solar filter here stops nearly all of the sun's energy from ever making its way down the optical tube. And no solar filter should be placed over an eyepiece like this with the scope's front end completely unprotected by a solar filter. The sun's heat through an eyepiece is concentrated and can damage the filter this way and the eyepiece, not to mention the difficulty of using it this way. And you can't point a telescope wide open at the sun and expect to look through the eyepiece with just these little solar eclipse glasses on. Remember these? The material in the solar glasses will melt and possibly catch fire. Your eyepiece can be ruined, and you will be blinded. Solar filters are not toys. We recommend them only for adults. H-alpha and calcium K-line narrowband filters look at the solar chromosphere and reveal features like solar prominences. Pretty cool, but these filters start in the neighborhood of $800 and up. Calcium K-line in particular are very expensive. Neither of these are recommended for beginning solar observers.
Beginner telescope packages sometimes include moon filters. Moon filters are nice to have. The light from a first quarter or full moon isn't dangerous, but sometimes it makes your pupils close up more than you'd like. Moon filters are an easy way to dim the moon's light, cutting glare, and allowing you to see a little more detail on the moon's surface. Set amount transmission moon filters allow a set amount of light to transmit through the filter to your eye. Sometimes you get a greenish colored one that comes as part of your scope package. The one on the left here in this photo came with my telescope. The one on the right is a 13% light transmission moon filter that has a grayish color. This color is much more common. Currently the 13% transmission filters cost $11.99 or thereabouts. There's a 25% version for $22.99, which allows a brighter image. You can also get variable polarizing moon filters. They come looking like two filters stacked together because they are two polarizing filters put together on a device that allows you to dial up how much moonlight you want to let through. When turned 90 degrees to each other, the filter turns quite black in the middle and blocks all light. These are nicer moon filters and tend to cost more money, $29.99-ish. For all of the moon filter prices I've quoted, we're talking about 1.25" eyepieces. If you want to get a moon filter for your 2-inch eyepieces, you can basically just double the quoted prices of those for the 1.25". Now we'll take a look at color filters. There are multitudes of color filters available on the market. Color filters are used to bring out detail when observing the planets. Opinions vary on how much help they actually are. They can be expensive depending on the brand you get. They're probably more useful for experienced planetary observers with larger telescopes.
There are other filters, including nebula filters, light pollution filters, and other filters intended for use with photography. Before investing in these, keep your money and get some experience in the hobby.
There are several star maps and charts on the market. They come in a wide variety of sizes. They're useful for showing you what objects there are to see in or near any given constellation, and for helping you plan a way of finding your objects of interest. A good one for you depends in part on what finder you'll be using. For example, a finder scope has some magnification to it, so a chart with stars to dimmer magnitudes, magnitude is a measure of brightness, is better. Here we have just the legend from a Tirion's 2000 map. These maps list stars down to magnitude 8, which is fairly dim. The legend is in 2 halves here because it's about 22 inches wide. If you're using a dot finder, charts with stars to magnitude 6 or 7 should be fine. The Pocket Sky Atlas, which is the one that's open here, is a map like this. So is the Peterson's Field Guide. If you want to have information about the objects you're looking at right at hand, you may prefer something like the Peterson's. It has both star charts and some information about many objects. The Pocket Sky Atlas and Peterson's Field Guide are convenient portable sizes. This version of the Tirion Sky Atlas measures about 16 by 11 inches with pages that fold out. There are different versions of it with 22-inch pages. The Tirion's is detailed and has relatively large print, which can be a help for people with vision problems. There are other maps and charts. You might check a library, bookstore, or your local astronomy club's library before buying. Now we'll look at red flashlights. Why red flashlights? When you're out in the dark observing after being out there 20 to 40 minutes, your pupil expands to its largest size, allowing you to see more and better in the dark. If you need to look at a chart or change an eyepiece or have any sort of temporary need to see or look for something so you can go back to observing, a flashlight with red light is the best thing to use because your pupil won't close up as much as it would if you switched on a white light. With a flash of white light, your pupil closes right up again, and it can take another 20 to 40 minutes for it to open up again so that you can continue observing. With a flash of red light, you can get back to observing usually in less than a minute or so. If you had a red flashlight with a dimmer switch, that's even better. Sometimes you just want to quickly check a chart and get right back to the eyepiece. With very dim red light, you can do this. Some people find their eyes are less affected by green light, so there are green astronomy flashlights available as well. This is why some dot finders also have green dots and bullseyes as an option. Diagonals connect between your telescope and eyepiece to change the direction that light comes out. Some telescope types, refractors, and catadioptrics can leave you observing in uncomfortable positions when looking at anything that's very far above the horizon. Diagonals insert between the scope and eyepiece, using mirrors or prisms to deflect the image to the side so you don't have to contort yourself while observing.
Accessories can make your observing experience easier and more enjoyable. If you have questions about accessories, contact us at our website or by email.